Hello, hello, hello. Once again, we are moving on to our next topic, which is deductive reasoning and two-column proofs. So you had a brief little overview about inductive reasoning, and we talked a little about Sherlock Holmes and his incorrect verbiage on deductive. So now today we get to really get into understand what the heck was I talking about when I said deductive reasoning. So let's get this written down somewhere, please. Deductive reasoning is a logical process in which a conclusion is based on facts that are generally assumed to be true. Deductive reasoning we sometimes refer to as top-down logic, and you're going to see at the end of this video a specific kind of deductive reasoning which everybody does tend to drag, and that is called proofs. But we will forget that I said that at all and move on. So there are two laws that are associated with deductive reasoning that I want you to be familiar with. The first is the law of detachment, and this is if the hypothesis of a true conditional is true, then the conclusion is true. So if P, then Q is true. P is true, and it's going to be something similar to P, and then Q is true. So, oh my God, what is this woman talking about when I'm saying P and Q's, and what the heck am I saying? The first is going to be some true conditional statement, and it's going to be very general. But then I'm going to go very specific with my next statement. So for example, if the sun is out, then it is a hot day outside. We'll assume that that is a true statement, okay? So that's my conditional. So now I'm saying on Monday, the sun was out. That is my next statement that I'm going to be making. So there's at least two sentences here. And I'm going to ask you to draw a conclusion from that. Well, based upon the law of detachment, I can say, well, it was hot outside on whatever day I said, which was Tuesday. Okay, so the first statement is always going to be very specific, or sorry, very general. Okay, but then I'm going to make a very specific one here. Okay, so here's an example. If a student gets an A on a final exam, then the student will pass the course. So this goes for anybody. Now, that's not necessarily true for this class, but if, say, a student gets an A on a final exam, then the student will pass the course. So that's the general statement. Now I'm getting very specific to a specific student. I'm saying Felicia got an A on her history exam. What can I conclude? Well, based upon the law of detachment, I know Felicia's going to pass her history course. Well, let's now get into geometry, since lo and behold, this is a geometry class. If a ray divides an angle into two congruent angles, then the ray is an angle bisector. Well, now I'm giving, so that's a general statement. Now I'm getting very specific, using specific letters. Ray RS is dividing angle ARB, so that angle ARS is congruent to angle SRB. And if you were to draw that, you would find that those are two angles that are adjacent to each other. So what conclusion can I make? RS has to be an angle bisector, based upon that statement that I made originally. Since that first conditional statement is true, I can make some conclusions based upon that. Okay? The second we have is called the law of syllogism. So this allows you to state a conclusion from two conditional statements when the conclusion of one statement is the hypothesis of another statement. So P's and Q's. If P implies Q, that statement is true. And if Q implies R is true, what I can then is just take out Q altogether and say, all right, well, if P is true, then R is true. So what I'm seeing here is that this conclusion of this statement is a hypothesis of another statement, okay, with a new conclusion. So what's going on is really I'm just getting rid of this middleman here and going right from P straight to R. So let's do an example. If a figure is a square, then the figure is a rectangle. Okay, that's fair. If a figure is a rectangle, then the figure has four sides. Do you see how my then statement and my if statement are exactly the same? So essentially what we're going to do is get rid of those two statements and just say if a figure is a square, then the figure has four sides. Nothing about rectangles whatsoever. And we're allowed to say that because those two previous statements are true. Let's do another one. If a whole number ends in 0, then it is divisible by 10. If a whole number is divisible by 10, then it is divisible by 5. So again, once we see that the conclusion of hypothesis, which involves the divisible by 10, is the same, I can just, let's get rid of them, and go straight to our final conclusion, where if a whole number ends in 0, then it is divisible by 5. So hopefully now you have gotten a little bit of inductive, a little bit of deductive reasoning. I love this video. I think it is super cute. Just take a listen to it about the difference between the two.
Inductive versus deductive reasoning, a la Schmuck. As you may have heard, there is more than one way to skin a cat, although none of them are endorsed by PETA. In the same vein, there is more than one way to apply reason. For example, you may decide that it wouldn't be a good idea for you to skin a cat, because all living things are precious, and you may be incurring the wrath of God by so callously torturing one of his creatures. Or you might just realize that you've got too much homework to do tonight.
You got lucky this time.
Either way, there's a cat out there somewhere sighing a huge meow of relief. When it comes to reasoning, there are two main ways to do it: by using inductive reasoning or by using deductive reasoning. Deductive reasoning, otherwise known as the top-down approach, starts with a general statement, theory, or hypothesis, and then works its way down to a specific conclusion by examining various pieces of evidence. For example, if you hypothesize that Dr. Seuss hates cats, and you provide examples from the Cat in the Hat that you feel support that hypothesis, you can deduce that Dr. Seuss does in fact hate cats. And let's not even get started on how he feels about thing 1 and thing 2. Of course, it's a little more complicated when applied to an essay, because there are many more pieces of evidence to consider, but you get the idea. Inductive reasoning, or the bottom-up approach, starts with a small observation or question, and works its way to a theory by examining the related issues. It's a bit more exploratory by nature than deductive reasoning. Like, how does Dr. Seuss feel about cats? Well, he has this cat do some really dumb stuff, and he keeps getting it in trouble, and the kids get angry at him, and he looks weird. So yeah, Dr. Seuss doesn't seem like a big cat fan. So, how to apply these tools when writing an essay?
So we aren't really too interested in writing the essay, but it really, those ideas that apply to essay writing applies to math as well. But hopefully you got kind of the big idea there, using the example of the Dr. Seuss. What is it that I'm trying to show you? Inductive reasoning is really making a generalized statement based upon a number of observations. We are essentially guessing. We are looking for a pattern. For example, even though the numbers we saw were being multiplied by 3 in that one from way back when, where it was 3, 9, 27, 81, we still were guessing what the next couple numbers were based upon patterns that we were looking at. However, deductive reasoning, we are using known facts, we are using definitions, properties, it's putting in some type of specific logical order, and we get a conclusion knowing and showing that something is true based upon everything that we have come up with. Okay? We are proving something, and we're essentially making a rule, while the inductive reasoning was coming up with conjectures, and we were kind of guessing and trying to find a pattern with that. We're making rules. That's where theorems are coming into play. So speaking of theorems, we are slowly going to be approaching our proving section. That's what we're going to be doing in our application for this section here. You have seen quite a few proofs in our couple of other applications, but now we're really going to kind of hone in on some stuff. We need some very important properties, so make sure you are writing these down. Our first one is the reflexive property. The reflexive property says something like A is equal to A. And you might think that this is a very silly property, but it's very important and allows us to show if something is sitting up against each other, that we can say that they are true. Symmetric property, shared sides are going to be equal. The symmetric property says if A is equal to B, then B is equal to A. So we're taking the two things and we're flip-flopping them. The transitive property looks very similar to the law of syllogism that we just talked about. If A is equal to B and B is equal to C, then A is equal to C. Do you see how I'm saying, well, if A is equal to B and B is equal to C, A equals C, B is missing here. Okay, it's like saying if I'm the same age as Mr. Hatfield, and Mr. Hatfield is the same age as Mr. Hacker, even though that's not really true, then I can say that I'm the same age as Mr. Hacker. Okay, so that's what's kind of going on. I'm leaving Mr. Hatfield out of this situation altogether. Lastly, we have the substitution property, and that says if A is equal to B, then B can replace A in any expression. Again, we probably have seen the substitution property already. The other one we have here is the distributive property, where if we have something out front where there's a sum, or even if there is a difference, we can distribute that through. A couple of things, we not only have properties of equality, we have properties of congruence. So the reflexive property of congruence, if we're talking, say, about a segment, that means these two segments are going to be congruent to each other. These are super useful. Okay, I know it seems silly to say angle A is congruent to angle A, but when we start getting into showing that triangles are congruent in the very, very near future, you're going to want to remember the reflexive property. Symmetric property, again, same idea, allows us to take congruent segments or congruent angles and flip-flop them on either side of our congruent sign. And of course, the transitive property. Now, do you have to write every single one of these down? No, don't. Write down maybe an example of the congruence where it comes to the segments or with the angles. It's up to you, okay? All right, here they are. We are going to talk a little bit more in depth about proofs. These are arguments that use deductive reasoning, and we focus in on two-column proofs. And what we're going to be doing is on the left-hand side, we're going to make a statement. But on the right-hand side, we're actually going to justify that by using either a rule or a theorem or a definition that allows us to do that. So this is kind of how it's going to be set up. Now, given the measure of angle 1 is equal to the measure of angle 3, I'm going to prove something specific, like the measure of angle AEC. So this angle here, AEC, is congruent to angle DEB. Okay, so at the very top, we're going to do our statements and our reasons. That's how we set up our two-column proof. The first statement is usually our given statement. You can break it up into multiple statements, or you can use the same one. So for example, here our given statement was angle 1 is equal to the measure of angle 3. That was our reasoning, would be that's given to us. Okay, so that's something we know is already true. And then from there, you're going to go in some logical order. That's when you saw some of those other proofs in the past. We're going to go some way that's going to eventually lead to what we're actually trying to prove. So in this one here, measure of angle AEC is equal to the measure of angle DEB. Now all this stuff in the middle here, these are all going to eventually lead to this. On the right-hand side, we're actually going to be giving different definitions, or we can give the different properties, including the ones that we just talked about in the previous slides or so. Okay, so once you get to the application part, if you really need some assistance, please call your teacher over, whether it be me or Mr. Hatfield or Mr. Hacker, and get some help with these, because it does tend to get a little bit tricky with these, and we can show you some tricks of the trade as we're going through these. Okay, all right, that is it for today for this video. Go ahead and get working on that practice where we're looking at what's the difference between inductive and deductive reasoning. As well as our proofs coming in our application. Woo! All right, go ahead and stop the video.